Good evening, participants.
Good evening, sir.
Good evening, sir.
Good evening, sir.
Yeah, very good evening, Gopi.
Sir, good evening, sir. Good evening.
Yeah, very good evening, sir.
Dr. Venkatesh, sir, we will wait for a few more minutes.
Yeah, sure,
Let
sure.
the participant will be joining. Okay.
Yeah, sure, sure, sure. Venkata Subramanian, sir.
Yes, sir.
Sir, actually, Gopi sir has shared your questions.
Yes, sir. Yes,
I
sir.
have
He
seen
informed
the
that.
questions now only.
Okay, sir.
No issues. I'll be responding to it very shortly.
Oh, okay, sir. Thank you very much.
Thank
Yeah.
you. Thank you. Sir, actually, where are you from?
That is from Institute of Chartered Accountant of India, sir.
Okay. Chennai. Okay, fine, fine. So you're from teaching fraternity, right?
Yes, sir. Faculty in Auditing Department.
Super, super. Fantastic, sir.
Yeah.
Good evening to everyone. Shortly, we are going to start today's session. Before that, I just want to give more instructions to you. And today, in our FTP portal, we have uploaded the PPT for the first 2 day sessions, and we also updated the attendance for a few of the participants. And the attendance updating work is still going on. Within Sunday, we will update all your attendance for all the 6 days. So once attendance is updated means on the 6th day from 6:30 to 7:30, you will have your assessment. And in a FTP portal, Atal FTP portal, you have to take your assessment. So once the assessment is completed, then you have to give the feedback in the portal itself. Okay, so these are all this general instruction you have to follow. And even in between you are having any queries means you can post your queries in a chat box, and also you can post your queries in a WhatsApp group also. Even if you need any help regarding your certificates means, you can contact us at any time. Okay, thank you.
Thank you, Shamli ma'am. Dear participants, kindly follow the instructions. The only purpose is everyone should get your certificate. So kindly attend all the sessions without fail. Then only you will receive a certificate. The last day, if you ask any reason that I am using my another mail ID, I am using my personal mail ID, whatever it may be, you should attend. Before that, you can inform through the WhatsApp group that which mail ID you have attended. Then we can able to identify the participant name and college name. Okay, so kindly attend all the session, because if you attend 3 days or 4 days, then you can't able to get your certificate. 80% of attend must. So you should attend all the session to receive a certificate. Moreover, we will share all the details like PPT or queries, whatever it may be, we will share you as soon as possible. Thank you. Dr. Venkatesan, sir.
Yes, Gopi, sir.
Sir, you can start now, sir.
Yeah. Okay.
Let it be, they will join. No problem. You can
No
start
issues.
now. Okay.
Oh, okay. Okay. With your permission, I will start, sir. Thank you.
It's not my permission. You can start.
That is not an issue. Okay, fine.
Okay.
Okay, dear all, I hope you people are doing good today. Yesterday it was a beautiful session where we have seen the quantum algorithms. Today I'm going to take about we are going to discuss about the quantum cryptography. Okay, so when the word the cryptography arises, immediately the lovers of cryptography, Bob and Alice comes into our mind, right? Those two lovers, no, till now they didn't get married, and still we are there to provide a secure communication between Bob and Alice, right? So, since Bob and Alice are still alive, no, this quantum cryptography, okay, let us see how it helps them to securely communicate with each other. Okay, so today we are going to see about quantum cryptography, where again these both levers are coming into the picture. So throughout this presentation, we'll be talking about, or we will be trying to secure the information which has been transferred in between these two peoples. Okay, so for the past two decades, we have been trying to secure their transaction, which means that the information that has been transacted between these two levers, no, we were trying using the classical algorithms. Now we are going to try to safeguard their relationship with the help of the quantum cryptography. Okay, let me share the presentation with you people. Because I cannot change the names of Alice and Bob. So I'm going with the same name, okay? So the topic which we are going to cover today is quantum cryptography. Okay. So quantum cryptography is a groundbreaking technology which ensures the secure communication by leveraging the principles of quantum mechanics. So in this particular modern world, the communication security is very very essential for protecting the sensitive information in everyday activities, such as, yeah, we can take it as online banking, we can take it as secure browsing, even in cloud storage, even in medical records, and even car keys. Okay, so the classical cryptography, which is widely used today, it depends on the difficulty of certain mathematical problems like factoring the large number or by solving the discrete algorithms. However, the advancements in the quantum computing, like Shor's algorithm, it actually poses a significant threat to this classical systems, which is potentially a breaking widely used encryption methods like RSA. The quantum cryptography actually provides a solution by offering an unconditional security through techniques like quantum key distribution, which we call it as QKD, which uses the laws of quantum mechanics, which is securely transmits the encryption keys over a public channel by ensuring that any eavesdropping attempt that can be detected as early as possible. This revolutionary approach not only strengthens the communication security, but also it prepares us for a future where classical encryption may no longer be safe. So the communication security you enjoy daily was like the paying by credit card in a supermarket, where cell phone conversations, SMSs, email, chat line, online calls, uh, and etc. Okay, so will be whatever we do in online. No, we need to have a secure kind of communication. So the communication security actually underpins nearly every aspect of our daily lives, from paying with credit cards to accessing the government services, and also by managing the medical records. The classical cryptographic methods such as RSA or elliptic cryptography, which actually it relies on the assumption that certain mathematical problems are hard to solve. However, with the potential rise of large scale of quantum computers, these systems become vulnerable as quantum algorithms like Shor can factor large number exponentially faster than classical algorithms. The quantum cryptography, by particularly, we can say that through quantum key distribution, we can address these kind of vulnerabilities. So, unlike classical methods, what happens is this QKD does not rely on the computational assumption, but instead it ensures the security based on the fundamental laws of physics. Okay, by using quantum states, we can encode and transmit the keys, and also this QKD, which means that quantum key distribution, it actually guarantees that any interception attempt will disturb the system, making the eavesdropping detectable. This shift from computational to physical security is critical for ensuring the secure communication in the quantum era. The future proofing our system against the threat posed by the advancing quantum technology. The communication security is something we rely on constantly, often without realizing it. From paying by credit card in supermarket to secure the medical records at hospitals, our daily activities depends on the encryption to protect the sensitive information. So actually, you think about the secure browsing while shopping online, cloud storage syncing across devices, okay, or even electronic car keys. All this depend on secure communication, right? So the organization like banks, governments, and utility providers all together they rely on the secure internal communication for their operations. As our reliance on as we rely on digital system as it grows, it does the need for the robust security measures. However, the classical cryptography methods that underpin this system faces increasing threats from advancement in quantum computing. It is very crucial to develop technologies like quantum cryptography to ensure that the security we take for granted today, which remains the which remains very reliable in the future coming days, right? The classical cryptography like RSA or elliptic cryptography, which relies on mathematical problems that are difficult to solve, like factoring large numbers or computing discrete logarithms. Um, uh, or we can say that for computing the discrete logarithms, these methods, no, it have been highly effective because it is done by the classical computers, which requires infeasible amounts of time to break them. However, with the advancement of quantum computing, the algorithms like Shor's algorithm could efficiently solve these problems, which renders a classical encryption method insecure. So, additionally, the classical cryptography, which it cannot provide absolute guarantee against the advanced attacks, or it cannot guarantee the evolving computational power. This limitation actually it highlights the need for a new approach for secure communication, one that does not rely on assumptions about computational difficulty, but instead on the unbreakable principles of quantum mechanics. Next, we are going to talk about the QKD, which is nothing but it is a quantum key distribution. So the quantum key distribution is the cornerstone of quantum cryptography. It enables two parties traditionally in the sense the both the lovers I'm talking about, which is Alice and Bob, to securely exchange a secret encryption key over a public channel by transmitting quantum states. What makes QKD unique is like it relies on the laws of quantum mechanics. So any attempt by an eavesdropper to intercept the quantum state will disturb them, so revealing the presence of an attack. So QKD actually it uses a technique called polarized photon or phase encoding for transmitting the key. Once the key is securely shared, this Alice and Bob can use it with a classical encryption method like symmetric cipher to communicate securely. The classical key distribution QKD provides unconditional security as it is fundamentally impossible to extract the key without detecting it. So this ensure that even with unlimited computational power, the encryption actually it remains very safe. So let us see how Alice and Bob shares secret key with polarized photon. Okay, Alice, what actually he does is he prepares a sequence of photon, polarized each one in one of the four possible states of polarization, the horizontal and vertical, and two backgrounds for polarization. Bob chooses to measure the polarization. In one measurement, he tries to distinguish between horizontal and vertical polarization and the other in diagonal basis. So the quantum key distribution relies on transmitting the quantum state, such as photon, over an open channel. These states are encoded using properties like polarization or phase, and it has been measured by the receiver using the corresponding detection basis. The actual process includes several key steps, which I'm going to list it now. Number one is key transmission. Number two is measurement and basis selection. Uh, Number three is reconciliation. Number four is error correction and privacy amplification. So what we are going to do in key transmission is when Alice sends a quantum states representing the bits to Bob over a public quantum channel. That is what he is going to transmit. Okay. The measurement and basis selection, what we are going to do is actually the Bob, what he is going to do is he is going to measure the state using randomly chosen basis, either horizontal, vertical, or by diagonal basis. Okay. So what the state key reconciliation is doing is when Alice and Bob compares a subset of their bits over a public channel for identifying the match basis, and they are going to detect the potential eavesdropping. So in error correction and privacy amplification, what we are going to do is we are going to find the classical protocol where we are going to correct any errors and remove the leaked information to generate a secure final key. This secure key can then be used for encrypting messages over traditional channels, ensuring by both confidentially as well as we are going to ensure the integrity also. So QKD is a revolutionary step forward than the classical method by providing a level of security uh, which has been given by the classical regular systems. Here, this particular slide, what actually it does is it highlights the critical steps to ensure the secure quantum key distribution, despite of the errors caused by the imperfection of potential eavesdropping. To maintain security, it is assumed that all errors are attributed to eavesdropping interference. The process begins with actually the error correction using standard classical protocol to reconcile the difference between the Alice and also the Bob's key bits. So the privacy amplification actually it ensures that any potential information which has been leaked uh, to eavesdrop is minimized. So reducing her knowledge of the final key. The accompanying graph actually this particular graph what actually it illustrates the relationship between the error rate and the secure key generation rate. Okay, as the error rate increases, naturally the rate at which secure keys can be generated is decreased. So emphasizing the need to maintain the lower error rate in QKD. So altogether, these measures and security proofs validate the robustness of QKD, making it a reliable solution for secure communication. So actually this particular slide, no, it is a real world implementation of QKD. Okay. So am I audible?
Yes, sir.
Yeah.
Yes, sir.
Thank you. Thank
Yes, sir. We can hear you, sir.
you. Yeah. Actually, the this particular diagram, no, it has been QKD has been successfully implemented in various real world scenarios. Actually, this image illustrates a practical demonstration of free space QKD conducted over a distance of 144 kilometer between Palma and Tenerife in the Canary Island. Okay, the experiment highlights the feasibility of secure communication through free space channels, even across significant distance. On the left, no, allies set up in La Palma, which includes a tracking laser. Okay, which includes the uh, tracking laser, polarization compensation system, and GPS synchronization for time alignment. CCD is used for precise alignment of tracking beam, which ensures a stable connection. The quantum signal is transmitted through free space to Bob so that he receives the setup on Tenerife, which is 144 kilometers away from La Palma. So the Bob system actually located at an optical ground station. It utilizes a large telescope for precise reception of the quantum signals, along with polarization analyzers for decoding the transmitted keys. This experiment actually, what it does is it demonstrates the use of classical internet connection along the quantum communication for key reconciliation and other post processing tasks. The success of this particular setup is a crucial milestone in advancing secure quantum communication in real world conditions, and it also paves the way for long distance satellite based QKD and also for the global quantum networks. Now we are going to see polarization and phase encoding. The polarization and phase encoding are the two methods used in, actually it is the two methods we are using in QKD to encode the quantum information. Okay, so we are going to see what is polarization encoding and as well as the phase
माइनस
encoding.
माइनस तो फिर माइनस माइनस प्लस हो गए तो माइनस का ही हो गया प्लस का ही हो गया माइनस प्लस
Polarization encoding as well as we are going to see about what is phase encoding. So the polarization encoding, what it actually does is the polarization states of photon. For example, we can take it as vertical or horizontal, or we can take it as diagonal. It represents actually the quantum bits. So the polarization filter, actually it is used for encoding and decoding those states. And what this phase encoding does is uh, it does the phase difference between two parts of photon, which is used to encode the quantum information. The interferometric setups are mainly used to measure these phase differences. Both these techniques are widely actually used in QKD protocols and provide robust methods for encoding the quantum states securely for ensuring that any interception attempt is, so that we can easily detect if there is any interception. So here actually we are here it focuses on allied setup in a quantum communication system, especially the polarized photon source. The polarized photon source is a critical component in quantum key distribution system as it generates the quantum state used for secure key exchange. On the left, no, the schematic representation actually it shows the polarization mechanism where photons are produced and aligned in specific polarization states. These photons then transmitted by a single mode, which is otherwise called as SM, uh, through optical fiber to ensure the integrity of the quantum states. The image on the right actually displays the actual hardware used for photon source, demonstrating its precision engineering designed for reliability in quantum experiments. The polarization control actually it ensures that the photons carry the intended quantum information, which informs the basis for I would say that for secure communication. Yeah. This technology actually plays a vital role in creating a robust quantum key distribution system, enabling the generation and transmission of quantum states with minimal errors, or otherwise we can reduce the interference also. The single photon sources are very crucial for QKD as they ensure secure transmission of quantum information. The most common technique for generating the single photons, which includes the parametric down conversion and attenuated lasers. The parametric down conversion actually what it does is a nonlinear. It is nothing but it is a nonlinear crystal, which is used to split one high energy photon into low energy photons. And attenuated lasers are dimmed to such a low intensity that the probability of emitting more than one photon at a time is minimized. These sources ensure that only one photon is transmitted per signal. So, by transmitting only one photon per signal, we can reduce the vulnerability to attack, such as photon splitting. The single photon source play a pivotal role in maintaining the security and reliability of QKD source. So we must ensure that this photon, if it is getting splitted also, we need to transmit only one photon at a time. So this is the polarization analyzer with single photon detector. Okay. So this is for your reference. Okay. The key components and functioning of single photon detector, which are essential for quantum communication system. These detectors no, are mainly used to identify and measure the individual photons by ensuring the accurate reception of quantum signals in protocols like QKD. The first type, the photo multiplier tube, which we call it as PMT, is highly sensitive detector that operates by converting the incident photons into electrons. So we are going to convert the photons into electrons using a photocathode. These electrons are then, after converting these photons into electrons, next we are going to uh, amplify it through a series of diodes, producing a measurable electrical signal. These photo multiplier tube are renowned for their high sensitivity and fast response, by making them suitable for low light applications. though they are typically bulkier and and it is very less robust than a solid state alternatives. The second type is avalanche photodiode, which is otherwise called as APD. Actually, we are seeing this particular diagram, which is nothing but it is an avalanche photodiode. These APDs actually work by operating in Geiger mode, where a single photon triggers an avalanche of electrons hole pairs through a strong electric field applied across the diode. Actually, this process results in detectable pulse of current, and avalanche photodiode, no, they are very compact and they are very efficient, and also they are widely used in modern quantum communication setups due to their ability to achieve high detection efficiency while maintaining low noise levels. Both photo multiplier tube as well as avalanche photodiode are fundamental to the success of quantum communication systems. As why? Because they allow for the quantum computation. Actually, they allow for the precise detection of the quantum states, which has been transmitted in a secure key exchange process. Okay, so this is how we are going to uh, securely transmit the data. So here in this particular slide, you cannot see anything without, other than city which is raining, and you can see um, a green beam that has been passing, right? So actually what it does is Alice and Bob are trying to communicate with a certain distance. Actually, this green line indicates the photons that are polarized. The indigenous population actually survive in this particular city. What Alice does is he sends photon. Those are polarized, which cannot be seen in eye. We cannot see in a normal eye. The green line indicates the position, and you need to know in what angle is receiver is set. So this is the receiver. Okay. So actually, from the center beam, no, the with the help of the center beam, actually the other stations which are in and around allies, it receives it. In this particular experiment, you can do quantum cryptography and also quantum key distribution, and also we can compute the hash function to do more fancy quantum communication. This is the quantum channel which is established between two parties, Alice and Bob, over a distance of 143 kilometer, because Alice stays in La Palma and Bob stays in Tenerife, which is 143 kilometers in distance. Okay. The polarization encoding is a fundamental method used in quantum communication to represent and transmit the quantum information. Actually, in this technique, the polarization state of photons light particle is utilized to encode actual data. The photons can be polarized in different orientations, such as in horizontal manner, we can, it has been oriented, whereas in vertical level it has been oriented, or at specific angles it will be oriented. And this polarization states, no, it serves as the basis for encoding the quantum bits, qubits. Otherwise, the quantum bits are otherwise called as qubits. In phase encoding, the polarization state, such as plus 45 degree or minus 45 degree, it can be used to represent binary 0. While plus 135 or minus 135, it will be it has been represented as a binary value as 1. The allies prepares this polarization state and transmits them through a quantum channel. The relative phase difference between the consecutive pulses encodes the quantum information by making it resistant to interference and also suitable for long distance communication. While at Bob's end, an interferometer is used to measure the relative phase, allowing him to decode the transmitted information. To further enhance the security, measurements are performed using detector based orient. For measurements will be performed using detector bases oriented at specific angles such as 45 degree or at Z basis at 0 or 90 degree. This ensures that any eavesdropping attempt by a third party, like so if they are introducing any any unwanted messages, the detectable errors due to the non-cloning theorem and the disturbance caused in quantum states. This method actually, it combines the advantages of phase encoding with polarization states, which enables the robust and as well as the secure quantum key distribution even in challenging transmission environment by paving the way for advanced quantum cryptography systems. The plug and play scheme is a practical and efficient setup in quantum key distribution system that ensures the secure transmission of quantum information between allies, and allies is the sender, whereas Bob will be the receiver. This particular scheme actually leverages the bidirectional transmission line, allowing light to travel from Bob to allies and then back to Bob. By simplifying the alignment and by synchronizing the system. Actually, in this particular setup, the Bob initiates the process by sending a light pulse through a beam splitter, which is otherwise called as BS. The pulse passes through a polarization beam splitter, PBS, and travels down the transmission line to reach allies. From ally side, the components such as Faraday mirror, FM, a delay line, DL, and a variable optical attenuator, which is nothing but VOA, come into the picture. The Faraday mirror actually, it ensures that any changes in polarization during the transmission are automatically compensated with the pulse that has been reflected back. The delay line actually, it introduces the control time shifts, and the variable optical attenuator actually, it attenuates the light pulse to the signal photon level for secure quantum communication. Once the pulse is modulated by allies with quantum information, it has been sent back through the transmission line to Bob, and the Bob actually uses his beam splitter, which is BS, and also PBS, and also detector, which is D0 and D1, to measure the quantum states of the returning pulses. The system actually it ensures that error from transmission line, it imperfections or it ensures that the imperfections are very much minimized. Okay, and also it ensures that the bidirectional nature allows for for automatic compensation of disturbances like polarization. Actually, it changes by improving the reliability and also the practicality of the QKD system. The plug and play configuration is especially useful for the real world QKD implementation, offering a robust and user friendly approach for achieving the secure quantum communication over optical networks. Actually, this picture actually showcases the ID Quantic Clavis 2 QKD system, a cutting edge solution for secure quantum key distribution. This Clavis 2 actually it is developed by ID Quantic, which is designed to implement the quantum key distribution in a highly secure and practical manner by making it a vital tool in modern cyber security. Okay, so this is the uh, a, a photo of Clavis 2, which actually it is it actually uh, designed for implementing the quantum key distribution. It is very very important when you want to have a secure communication, and if you want to generate a QKD, then this particular setup is very very important. Actually, this system uses quantum properties such as superposition and entanglement to ensure the encryption keys that are shared securely between two parties. If an eavesdropper or if an intermediator is attempting to intercept the quantum channel, the laws of quantum mechanics, it guarantees that their presence will be detected due to the disturbance introduced into the system. So actually, this particular system actually it ensures no the disturbance caused by the third party. This Clavis 2 actually it provides a complete end-to-end solution combining a quantum channel for key exchange and a classical channel for authentication also. Actually, it includes components such as single photon source, detectors, and also a robust control system for managing the entire process. This system is a modular, allowing flexibility in integration with existing network infrastructures. Actually, it is widely used for secure communication. I would say it has been used in industries uh, like banking sectors. They are using it in government sectors. Again, yes, they are using it, and telecommunication. Yeah, they are using it. So for ensuring the future proof protection against threats, they are including those from quantum computers. Actually, this particular image it represents the idea of quantic Cerberus system, a landmark development in the field of QKD. I mean, when we are thinking about commercializing the QKD, this particular Cerberus system, no, it is a landmark thing which was introduced in the year 2010. This particular system it has been marked as a significant step forward in making QKD technology accessible for practical use in secure communication networks. The image actually it is sourced from Swiss Quantum, which highlights the system application in real world scenarios. The Cerberus system actually it was designed to facilitate the highly secure encryption by leveraging the principles of quantum mechanics. Actually, it ensures that cryptographic keys are exchanged securely over a quantum channel with the guarantee that an eavesdropping attempt will not be eavesdropping attempt will be detected. Okay, the system employs actually this particular system employs the polarization or phase encoding techniques, and also it integrates the advanced components such as single photon source, again detectors, and also the robust classical communication protocol for key reconciliation and privacy amplification. This particular slide actually illustrates QKD based secure communication scenario which involves two users, Alice and Bob, and a trusted node. Here is how the interaction takes place. Okay, so Alice actually it is so user 1 and user 2. You can take this particular thing as an Alice and this particular user as an Bob. So this is user 1 and this is user 2. Okay, so the user 1 is actually he has been equipped with a key called K1, interacts with the trusted node through QKD link. Similarly, user 2 uses the key K2 which communicates with the same trusted node. The trusted node acts as an intermediary for secure communication between these two users, user 1, user 2, or otherwise we can call it as Alice and Bob. So to securely relay the information, the trusted node actually it XORs the key 1 and key 2, and it creates an intermediate value that is then transmitted to user 2. So we are XORing the K1 and K2 here, and we are transmitting this XOR result to the user 2. So upon receiving this XORed value, the user 2 actually what he does is he performs an additional XOR operation with their key K2. The final XOR operations cancels the K2, leaving K1 as the result. So this process actually ensures that user 2 securely reconstructs K1 without any direct transmission of K1 across the network. So by leveraging the principles of quantum key distribution, the system guarantees that the key remains secure, and if at all any attempt has been made by the third party, it can be detected, and we can preserve the integrity and confidentiality between the two users, namely user 1 and user 2. This particular slide or this particular diagram actually it illustrates a trusted node network designed for secure TV conferencing as presented by the two researchers, and one guy is Sasaki, okay, and another guy is a research scholar of Sasaki, and they have done this particular research in the year 2011, and they have they have presented a paper also. Actually, this system architecture, what it does is it integrates the three critical layers: the quantum layer, number one, the key management layer, number 2, and also the communication layer, which is number 3. The quantum layer, what it does is it actually employs the quantum key distribution to securely generate and exchange the encryption keys, ensuring the highest level of security by leveraging the principles of quantum mechanics. This guarantees, by leveraging the principle of quantum mechanics, we can guarantee that any attempt to the intercept or the third party and the key transmission would be detectable, and it will be providing an unbreakable security foundation. The second layer, the key management layer, what it does is with its central key management server, which is otherwise called as KM, which is this particular KM is actually it is responsible for this particular KM is actually responsible for what to say, mm, uh, for distributing, and it will be distributing the keys, as well as periodically it will refresh the encryption keys used for the communication. This particular server actually it ensures that the encryption keys ensures the particular encryption key which to remain secure, and are also updated throughout the conference to maintain the confidentiality. The communication layer, the final layer, after refreshing the encryption keys, it encrypts the video, audio, and also the control data, and ensuring that all aspects of the conference, from video streams to sensitive discussions, are securely transmitted. This trusted node network architecture not only enables the security in TV conferencing, but also it provides protection against the third party by ensuring the confidentiality and integrity, even in the presence of potential quantum level threats. So here is the video representation. You can lay one ground station to establish a key. This is our globe, where the user establishing a pair of keys with the flying of light flied over between the satellite and the ground station. So in this particular video, you will be I'll be playing this particular video where you'll be seeing a satellite line over one location to establish the connection over another side of global, global, which establishes another pair of key between the satellite. Each station which is available in this particular video has many keys for distribution, and many pairs of ground stations are established, and this particular thing, it only takes one satellite to over the key distribution network. So let us watch this particular video. So here we are user is establishing a pair of keys with the flying of light between the satellite and the ground station. And you'll be you can able to see a satellite line over one location to establish connection over to another side of globe. each station will be having many keys for distribution. So many pairs of ground stations are established here. So one satellite will have only one key to distribute over the network. So now what we are going to do is we are going to make a small part of satellite with a single photon detector with 4 channels. So these are the channels we have. It is actually designed to detect the individual photons in a quantum system. The 4 channel setups, what it does is it allows the simultaneous detection of multiple photon signals, improving the system sensitivity and also the efficiency in experiments involving the quantum communication and quantum cryptography or quantum imaging. Each channel in the detector is capable of identifying single photon, which is crucial for accurate measurements in quantum systems, where photon count actually it rates count rates are extremely low. The prototype actually plays a key role in enabling the advanced quantum technology by providing high performance detection with low noise and fast response time also. And it is essential for applications like quantum key distribution and also for performing secure communication between the two users. So now we are going to see about quantum hacking. So the quantum cryptography partially, particularly we can say that the quantum key distribution is theoretically secure due to the principles of quantum mechanics. Real world systems are not very much immune to attacks. The quantum hacking targets uh, actually these kind of implementation actually flaws such as yeah, there may be a flaw. Okay, because of this particular hardware, um, due to imperfection in hardware or the detectors or the protocols rather than breaking the quantum principles. So the quantum key distribution actually it ensures the secure communication between two parties. Traditionally, we can take it as allies and Bob. The central premise is that any third party attempt by has been made. No, actually it introduces the uh, introduces the detectable disturbances due to the principles of quantum mechanics. The security key rate, no, which determines the effective rate of effective effective rate of secure key generation is a function of quantum bit error rate, which is otherwise called as QBR. Uh, Higher QBR actually it indicates the potential of
Participant, kindly mute your audio. Participant, Google sir, Google sir. Yeah, it's okay now.
yeah. So the higher rate of this particular QBR actually it indicates the higher potential of third party involving in the particular transmission, or otherwise it indicates that there is an imperfection in the hardware. The security of QKD is guaranteed by a combination of the laws of physics, which prevents undetected interception of quantum states, and a detailed model of the equipment, ensuring that the implementation vulnerabilities are accounted for the same. This particular robust security proof actually it enables the quantum key distribution to provide an unconditional security for cryptographic application. This is the iterative process which has been involved in strengthening the security proof of QKD by developing a model of the equipment which represents the expected behavior and also the specification of quantum devices. The potential vulnerabilities are identified through hacking attempts where adversarial techniques actually exploits the imperfection in the implementation. These discovered errors or flaws are after that it has been analyzed and integrated into the security model by ensuring the updated model reflects the real world conditions. This particular iterative approach, no, it enhances the robustness of QKD system by continuously refining the security proof to account for both theoretical as well as practical weakness. Ultimately, we can fortify the system against a sophisticated quantum hacking strategy. The key steps which has been involved in quantum hacking are discovering vulnerabilities in the practical implementation of quantum devices such as imperfection in hardware or flaws in protocols. Once these weaknesses are identified, the researchers demonstrates the attacks that can exploit them, showcasing how an adversary might compromise this particular system. The next step is to develop the countermeasure to mitigate these particular vulnerabilities by ensuring the system resilience against the potential potential threat. And finally, I would like to say this countermeasures are implemented to eliminate the imperfection, leading to a more secure as well as the robust quantum communication framework. Next, we are going to see how we are going to uh, counter. What are the countermeasures that are available for QKD attack? To address this particular vulnerability in QKD, the researchers have developed several countermeasures to strengthen the security of this particular system. One is randomized detector sensitivity, where it has been where we can prevent the detector blinding attacks by varying detection threshold. And next one is decoy state protocol. And the third countermeasure is the measurement device independent QKD, where we can eliminate the vulnerabilities in the detection process by relying on untrusted measurement devices. These countermeasures actually it ensures that QKD system remains secure against both known and also upcoming. Rather I would say it is emerging attack strategies, reinforcing the practical viability of quantum cryptography. And this is the quantic clavis 2 QKD system, which we have, I mean, actually we have discussed this particular clavis 2 QKD system in the previous slide. In this, quantis random number generator has been fixed. In this particular system, we have fixed a random generator. So this is the random generator where we have fixed in clavis 2. So now So this is the random generator. Now we are going to see about Trojan horse attack, which is a vulnerability in quantum communication system where an third party, if we tries to inject a powerful external light pulse into user one device through a transmission line. Okay, these pulses actually interrogates user one phase modulator, and by analyzing the reflected or leak light, we can directly infer Alice bit values, which can directly infer the Alice information. So to carry out this particular attack, the Eve's equipment is strategically placed in the transmission line, exploiting the hardware imperfection and insufficient attenuation with user one system. So such attacks actually it emphasize the importance of robust countermeasures by including the effective attenuation and carefully monitoring of incoming signals, and it also monitors the active detection mechanism has been deployed to identify and block unauthorized pulses, so that it ensures the integrity of the quantum communication system. So by in a layman word, by incorporating this particular equipment inside the system, we can directly uh, find if there is any attenuation or if there is any uh, signals that are incoming during the communication, or those kind of steps we can easily identify. In this particular actually what you are seeing is are the these are the different types of attacks on quantum computing. Okay, so which targets on various components. So these are being tested in different systems, uh, like quantic and securenet. Okay, these are the different types of attacks that has been uh, done in quantum machine. Okay, so here we are. I would like to showcase a simple attack example which targets avalanche photodetector (APD), which is commonly used in quantum communication system. Actually, this particular graph, what it does is it plots the relationship between the breakdown voltage, which is nothing but VBR, and the bias current ITH, and comparing two operating modes of APDs, which is linear mode and Geiger mode. In Geiger mode, the APD operates above the breakdown voltage. Okay, this is the Geiger mode where it operates um, above the breakdown voltage, which enables us to detect the single photon with high sensitivity. However, this particular mode is susceptible for an attack such as detector blinding, where an adversary manipulates the uh, avalanche photodetector by adjusting the bias voltage or by injecting a strong light pulse to force into a linear mode. So in linear mode, the APD actually loses its single photon detection capability, allowing an attacker to bypass the quantum security protocol. This actually what it does is it highlights the critical need for secure biasing and monitoring of APD to prevent such attack and also to maintain the integrity of the system. The faked state attack in avalanche photo detector operating in linear mode, where an attacker exploits the system for manipulating the detection outcomes. In this particular attack, the attacker actually he intercepts and also he measures the allies quantum signal and determining their quantum state, and also then he prepares and sends the tailored or faked state to Bob, which ensures that the detector clicks only under favorable condition to her. Okay, if and only if Bob chooses the same basis as attacker during the measurement, the detector will click, and Bob bit will value will match the one that has been sent by the attacker. This actually ensures that Bob and attacker share the identical basis and bit values, creating the illusion of secure communication. And by doing so, however, if Bob becomes or if Bob chooses a different basis, then attacker uh, click will not occur, and the bit is discarded during the classical post processing. Actually, through this particular method, the attacker can completely bypass the security of the quantum channel effectively by gaining full knowledge of the shared key without introducing the errors that Alice and Bob could detect. This attack actually it underscores the importance of robust countermeasure such as active monitoring and detector security in order to prevent the manipulation of APD in quantum communication system. Actually, this is the outline of a significant eavesdrop event that has been on a quantum key distribution line, which has been installed at National University of Singapore NUS campus on July 4th and 5th of 2009. Okay, in this particular scenario, Alice and Bob, the legitimate communicators, are connected via 290-meter fiber optic cable. Okay, which is part of the secure QKD system designed for sharing cryptographic keys. However, the system was compromised by an attacker who successfully intercepted the entire key distribution process and achieving 100% eavesdropping on the QKD line. The setup involved several security stations labeled S12, S13, S14, and S15, which are uh, critical points along the fiber cable that are potentially involved in the interception or compromise of the transmission. The QKD line was designed to ensure a secure key exchange between Alice and Bob. But the eavesdropper, what he did is he exploited the vulnerabilities in the transmission medium or on the system to gain the full access to the quantum keys, undermining the security measures in place. Actually, on performing the entanglement based on QKD Eavesdropping with 100% key on installed QKD line is shown in the next between Alice and Bob, where the we have shown the communication line. Okay, this graph actually it is a time versus bit rate with and without eavesdropping. Uh, it shows the performance of the QKD which is not affected by eavesdropping. And there are several other countermeasures are available to detect the attacks, such as to detect the sensitivity. We can monitor the extra electoral parameters in the detector, and also we can detect the dependency among the devices. So this is the ID Kerberos system, which utilizes the dual key agreement. So it uses the dual key agreement by combining the strength of QKD and also the classical cryptography to ensure the secure communication. And this particular diagram actually demonstrates the uh, several distinct approaches where QKD along with BB8 4 protocol. Okay, so this is one of the first and most widely used QKD protocol for leveraging the quantum mechanics to securely distribute the cryptographic keys between user 1 and user 2, which is Alice and Bob. So it ensures that any attempt to intercept the key will be detected, providing an extra layer of security. So BB84 protocol actually it ensures that if there is any attempt has been made to intercept the key, then it will let us know. Okay. Next approach is public key infrastructure, which is PKI, along with RSA 2048, which is a widely used public key algorithm for secure data transmission. In this particular public key algorithm, the system uses this particular RSA 2048 to securely exchange the key over an insecure channel, which relies on the difficult of factoring the large numbers. Another distinct key approach is a symmetric cipher with along with AES, a widely trusted symmetric encryption algorithm which has been used to encrypt the data. Once the security, once the secured keys are established. Okay, so this particular AES is actually it is efficient and secure for encrypting the bulk data in the commercial system. So the combination of QKD for secure key distribution along with RSA 2048 for public key cryptography and also along with AES for symmetric encryption, it makes this particular Cerberus and robust system. However, despite its advanced security feature, the potential for eavesdropping again it still exists. If any part of the system, either in BB84 or RSA 2048 or in AES 256, if there is any compromise, again we will have that particular vulnerability. Uh, so I would like to say that quantum cryptography is viable complement to aging classical cryptography method, where quantum cryptography as an implementation of imperfection and the research community handle this particular problem successfully by finding out a lot of methods to solve this particular vulnerability. So the advantages of using this particular quantum cryptography, it offers several advantages when we compare with the classical cryptography method. So the one is unconditional security. Number two is future proof against quantum computers, where it protects against quantum attacks. And also, based on this, we have an threat over the classical cryptography. And finally, we will have a global implementation feasibility, which has been demonstrated through free space and satellite based QKD experiments. These advantages actually it makes quantum cryptography a cornerstone for the future of secure communication, and also it ensures the sensitive data remains protected in an increasingly in this particular digital world. And we are going to see what are the challenges in implementing the quantum cryptography. Despite its promise, the quantum cryptography actually it faces several challenges in cost wise, which is very high in its initial investment for procuring the specialized hardware like single photon sources and also detectors. And next challenge we are facing is the scalability, where it is very difficult in deploying the QKD system over large distance without trusted nodes or quantum repeaters. So with the help of the trusted node and also with the help of the quantum repeaters, we can connect the long distance. Whereas without this, it is highly impossible to cover a larger distance. And the final challenge we are facing is the integration, where we need to ensure the compatibility with existing classical communication network where it is not done yet. So addressing these particular challenges, actually it requires ongoing research and innovation, and also we need to include the development of uh, cost effective hardware and also the scalable protocol and seamless integration method to make this quantum cryptography widely accessible. So these are the thrust areas where the people who are willing to work on the quantum computing in cryptography, we can. These are the three main thrust areas where we can concentrate on. And the future of quantum cryptography is bright, because the 6 days faculty development program is not going to be waste. It is very bright. In forthcoming years, in 2 or 3 years, this particular quantum cryptography is going to again come back with a bang, along with the advancement in technology and also in infrastructure, by paving the way of for widespread adoption. So actually, the key development, which also includes the satellite-based QKD networks, which enables a secure communication uh, across the continent. And the second development I would say is integration with post-quantum cryptography, which combines the quantum as well as the classic technical for hybrid security model. And the third future development, which I would say is it is advances in quantum hardware, because this is the place where there is a lot of chances of malfunction that can be happened here. So it is a we can design an hardware which is a miniaturized single photon source and detector for cost effective system. As this innovation mature, the quantum cryptography will become a fundamental part of global communication network, and also for securing data against both current and future threats. So the collaboration between the government as well as industry and as well as the academicians like us will play a vital role in driving this transformation, and this particular dream will come true uh, if we concentrate mainly on this particular developments. Okay, so the only thing is the academician like us is the driving force to make this particular things happen. Yeah, thank you. At, at the outset, no, I would like to thank Professor Gopi and his team for arranging this FDP in a successful manner, and it is going to be, conducted for next 2 days. Okay, so I'm really happy and thankful for the coordinator and his team, as well as Dhanlakshmi Srinivasan Engineering College for providing me a wonderful opportunity to spend my time with you for 2 days. Gopi sir? Gopi sir, you there?
Sir, thank you, sir. Thank you for presentation, sir. Thank you very much.
Yeah.
I
It
think
is
Gopi's
already
call is
time, I think so.
Thank you, sir. Gopi's in another work. Thank you, sir. Thank you very much, sir.
Okay, no issues. It is already time actually. If there is any doubt, you can post your doubt to the coordinator so that I will answer those questions. Okay.
Okay, sir.
Thank you, participants. I have taken most of your time because 7:30 you got next session. It is already 7:32. Sorry for that.
So no issues, sir.
Thank you very
Very
much.
interesting. Thank you, sir.
Sir, Venkata Subramanian sir, do you have any? If you have any doubts, you can post your questions to Gopi sir.
Okay, sir. Sure, sir.
Yeah, I will mail you. No issues.
Okay, sir.
Yeah.
Dr. Venkataswamy sir already posted one query. I will copy and paste and share you,
you have
sir.
already sent those questions to my WhatsApp. No issues.
Okay, sir.
Gopi sir, thanks for
Thank
providing
you
this
so much, sir. Thank you
wonderful
for your
opportunity.
wonderful presentation.
Thank
And
you.
almost 240% daily party attending the session.
Yeah,
I'm very
yeah,
happy for this.
yeah. Because this is, quantum computing is going to rule.
The world.
Yeah. For
Yeah,
the
it will be
next
going to
decade.
rule the world next 10 to 15 years.
Yeah.
There is no compromise for that.
No other option.
No other option.
Yeah,
After ADS or AML,
yeah.
next will be going to rule the world. Entire
Is
world is quantum computing only.
quantum computing. Yeah, for sure.
So basically, as a CSE or IT or ADS, what it may be, we have to learn what is quantum computing and other things.
Yes.
Yes.
Thank you, Gopi sir.
Thank you, sir.
Sorry
Dear
for so much of time taken.
No. Actually, I am very happy to share the information like a resource person like you, and I just want to tell you a few things.
Yeah.
The thing is, while choosing the resource person, I am in a dilemma where I have to choose.
Okay.
that is a very big
Actually,
incident happened in my department.
the resource persons for the quantum computing, no, they are very, very less.
Yes, I know that. But
Yeah,
everybody is learning, no?
you have got all the resource person.
Yeah. I asked
who
few
is,
more members from Kerala as well as Karnataka Presidency University So many engineering colleges I asked regarding this quantum computing. They told that, sir, I am not aware about the quantum computing.
Yeah.
You can look into other resource person.
Okay. Fine.
So I spoke almost 20 to 25 members. But
Okay.
anyhow, it will be happy for our institution also.
Yeah. Thank you very much, sir. Gopi sir.
Yeah.
It is my honor to serve you.
Yeah,
No issues.
to be honest, I will be honored to you
Yeah.
because what to say, there is no words because choosing resource is very difficult for me while applying Atal FDP.
Yeah. Okay.
Yeah. Okay. Thank you
Thank you
so
very much,
much,
sir.
sir.
Thank you.
Thank you, sir.
Yeah.
Dear participant, we have 5 to 10 minutes. Wait for next session to be going to start. We will wait for our next resource person, Dr. Mani Padmanabhan, VIT Vellore. You can take 5 minutes break for the next session. Thank you.
ಸರಿ ಸರಿ ಓಕೆ ಓಕೆ ಕೊಡ್ತೀನಿ ಒಂದು ನಿಮಿಷ. ಆಯ್ತು ಮೇಡಮ್, ಕಳ್ಸಿಕೊಡ್ತೀನಿ ವಾಟ್ಸಪ್ಪಲ್ಲಿ. ಅವರಿಗೆ ಯಾಕೋ ಇವತ್ತು ಜ್ವರ ಬಂದಂಗೆ ಆಗಿದೆ, ಅದಕ್ಕೆ ಮಲಗಿದ್ದಾರೆ. ಹೌದು ಮೇಡಮ್. ಇಲ್ಲ ಪರವಾಗಿಲ್ಲ, ಇಲ್ಲ ಪರವಾಗಿಲ್ಲ. ಓಕೆ.
Yeah, Gopi sir and other participants, very good evening to all. Gopi sir, let's start.
Mani sir, shall we start?
Yes, madam. Yes, madam.
Okay, sir. Thank you, sir.
Dr. Mani
Madam, my screen time
Padmanabhan.
is-
Dr.
Yes,
Mani
yes, sir,
Padmanabhan.
yes,
Yeah,
sir.
thank you very much for your next session.
Okay.
I am very happy to share this session will be also more useful for the participant. Go ahead with your presentation. Dear participant, if you have any queries, you can post in chat box, or if you have more number of queries, you can share to the mail ID. We will get back to you within a day for your queries. Okay. So next session will be going to start. So all the participants come back and join the session. Thank you very much.
Thank you, sir.
Sir,
Thank you, sir.
sir, you can start your session, sir. Thank you, sir.
Yes, sir. So very good evening to all. This is my second section. Yesterday we started with the quantum information theory. In this quantum information theory, we discussed about a few more theorem and other topics. So this is my agenda for today's presentation. Today, I just give the fundamental overview of quantum simulation. What is quantum simulation, and the purpose of quantum simulation, key aspects of quantum simulation, and other quantum channels, how to create your simulating quantum channels, and CBTB map, types of error in the quantum simulation, some applications of random error, and also three more theorems we will be discussing today. That's a data compression theorem, communication theorem, direct coding theorem. Finally, we'll discuss about what is the basic difference between your classical simulation and quantum simulations. So these are the topic I am decided to cover for the next 1 hour for all the faculty members. So here, basically, the simulation, the quantum simulation refers that you have to be taking care about the software testing part before we are going for the quantum simulation. So in the software testing, if you are taking for the test cases, it will be playing a major role. We want to be created test cases in the sense we need a clear input and what will be the output and what will be the process. These three are the major components. For example, you taking as a quantum simulation also, the qubit A and qubit B will be providing as an input, and with the operators, different operators, it will be providing as a qubit C. Qubit C in the sense you have to be understand what is the sequence and what is the flow of the qubits. Okay, so what are the quantum simulations? All those things you have to be clearly you have to be understand. So the quantum simulations says that the clear study of the qubits and what are the process of the particular process, particular activity. So the quantum informations it will be provided and exploring the data. Critical as well as how the analytics, how the data will be added over there, and what will be the expected outcome. That's a predictive things will be available. So we have to be understand. So what is the process it will be going on, and what is the flow it will be going on in the quantum process. Because without understanding, we cannot create the test cases. So even for the small programming test cases or other things also, here also we need to be identify error. So basically, if you want to identify the errors in the qubits, error in the quantum simulation, then you have to be understand the clear understanding of the process. So understanding the process and the predictive the what will be the expected outcome, and what are the inputs you have to be providing. So all those things you have to be analyzed. So Basically, that quantum simulations, it will be provided the clear study about the particular process in the quantum system. So it will be the a composite quantum system or a gentle measurement or any other process it will be happening in this sense. You have to be clearly understand all those things. So what is the purpose of quantum simulation? So basically, the quantum simulations, if you are moving with the quantum simulation, especially in the information theory, even in the last class also, yesterday we discussed about if it's a very small data, then we can deal with the DBMS and other systems. If it's a very larger information in the sense, it's very difficult to understand. Even we have a composite qubits also. Yesterday I explained about the composite qubits. So then we will be getting as a mixture of qubits and very complex data it will be getting, right? So modeling the complex of quantum systems, the simulation will be helpful. So the first purpose of the quantum simulation, it will be the modeling the complex quantum systems. So a number of the quantum systems are available in the sense it will be modeling over there, and we can study the quantum error. So wherever the error will be there, the noisy error, wherever, for example, the flow, it will be coming from directly, some error or some mismatches, it will be happening. Where the error it will be happening, that will be identified because of the simulation, the quantum simulation. And in the analysis part also, even before implementing the information or before implementing the data, so you want to be identify the algorithms. I mean, what are the flow of the algorithms? So the simulations will be needed. That is quantum simulations. It will be describing what will be the input, what will be the output, and what will be the major process for the particular process. And entanglement, yesterday we discussed, and also other resource persons also clearly explained about the entanglement. So it will be exploring the quantum simulations. Another purpose of the quantum simulation will be exploring the entanglement of data. So multiple qubits, if you are acting as a multiple qubits, a and a dash, two qubits will be available. It may be the different part, but you have to be understand what is the process will be there. And even reversible qubits we discussed yesterday. That is your with the help of the pair of gloves I explained. So these are the information that will be helpful while we are going to be understanding about the quantum simulations. And then optimization problem. Yes, the optimization problem, it will be helpful for storage. So we cannot store all the data in the single forum. So optimization will be the very important component. So if you want to be do the optimization, then the simulation, the quantum simulation will be the major part. So these are the different purpose of the quantum simulation in the information theory. So once the quantum simulation will be helpful for the modeling the complex quantum system and identify the error in the particular places, the algorithm development, entanglement or multiple qubits. Whenever you're using multiple qubits, it will be helpful. And finally, the optimization technique and security. So why we are doing optimization and other protocol related things in this is for the efficient security access only. So the quantum simulation, it will be helpful for the different criteria in the information theory. And what are the key aspects of the quantum simulation in our information theory? In the sense, it will be simulating the gates. So for example, different circuits and different gates you have to be simulate. Then that simulation will be helpful, and modeling, yeah, structure of the quantum system, you can identify where the process will be happening and what is the logic between one qubit to another qubit. So the qubit A will be there, then qubit B will be there. What will be the connectivity between the A qubit and B qubit? The modeling also you can understand. And error identification. So the particular process where the error it will be happening, and which place that the error it will be impacted, and what are the impact it will be happening if the error it will be identified. For example, that the error it will be identified in the initial stage in the system, you can rectify the problem. But the problem it will be running continuously in the sense it's very difficult to understand, and the problem it will be increasing. So the error identification process also the quantum simulation will be working. And other quantum preparations like gates, all those things, it will be so basically whenever you are decided to start or decided to designing your quantum simulations in this, the first of all you have to be design the quantum channels. So what is quantum channel? Here in this slide it will be explaining what is a quantum channel. So the quantum channels, it will be describe how your quantum information will be transmitted or transferring through the different channels. Even that all the qubits will be the qubit, it will be the different part of the places, the different servers will be available. So the different places of the server, all the qubits or all the qubit data are available. So during the transmission, how the transmission will be happening. So the data, how the qubit transmissions it will be happening, that will be described by the quantum channel. The quantum channel, it will be says that how the qubit transmission will be happening. So the simulations, basically the simulations will help to understand the quantum information, and also what are the error will be there, and providing the better correction of the error during your development itself. So these are basics about your quantum simulation. So here today's section will be discussing about the three major components, three steps for developing your or simulating your quantum channels. The step number one, you have to be identify the CPTP map. That is your completely positive preventive map. This CPTP map development will be the step number one for the simulating your quantum channels. Though the previous slide I explained about the what is a quantum channel. This is the transmissions. If you want to be understand with the DBM or networking concepts, the packet switching, right? So in concept, we are discussing about whenever we are teaching to the students of computer networks, the data transmission will be happening through the packets, right? So the similar concept only from the quantum technology also. The quantum channels, it will be the data processing between the one qubit to another qubit. How the qubits it will be traveling. So step number one, you have to be develop your CPTP map, and the step number two, you have to be identify what are the error will be the random error. You have to be identify, simulate the effectiveness. If the error will be happening, what are the problem will be gathered. So what are the error will be there, the random errors you have to be identify. The upcoming slides I will be explaining all the step number one and step number two, and step number three also identify the reliability of the input and output. That's what will be the difference between your expected outcome and the input. In the software test cases, input will be the A comma B. For example, the simple qubit operation A comma B. The C, it will be the output. Whether you're not getting a C, I mean, before development, we just inform the C it will be the output. But you're not getting the C value in the sense, then slightly some difference will be there. That's like how much percent of the difference will be there in the sense we can identify. This process, it will be called as a measuring the reliability of the output state and input states. So in this process, we are using as a trace qubits. We'll discuss one by one. For the next 30 to 35 minutes, I just explaining about all the three steps only. So the first of all, CPTP map. So that map construction will be the first process. So before you're going to be starting your map, that's a trace distance you have to be understand. So what is a trace distance? So we have a two component, two qubit will be there. A comma B, two qubit will be there. And the two qubits we can identify as a trace distance of A comma B. So the trace distance of absolute value and expected outcome, it will be the slightly difference in the sense they have some difference will be there. Even the yesterday's class, yesterday's FTP, I just explained about the trace difference as well as the entanglement difference. So slightly it will be difference in the sense it will be the same concept only we are using for the CPTP map development also. For example, this is a process we are going to be doing for our map creation, CBTP map creation in the sense. So it will be simulating and analyzing the quantum system and capturing all the trace. That's all the data it will be added. Your P, it will be the original original data informations or original quantum system will be available in the sense. We have to be traced to the P dash. That is your tracing of informations. And completely positive, what is completely positive? The next slide it will be explaining what is the completely positive data. So all the measurements, it will be converted as a P dash. So now we have the traced informations in our hand. So the traced information is also available. So here preventing the trace based on the density of the matrix. So if the A dash is equivalent to A in the sense there's no any error. If it will be the any slightly difference or any informations are not clearly it's not available in the sense we have to identify the error will be there. So then we have to do the prevention, or else we have to do the identify the what will be the error. Error will be there. So how can I identify the error? So trace based on the CPTB map, we just identify what will be the expected outcome. So this one each and because we have to be explained with the software testing only for the error identification. We cannot directly explain about all the concept with the quantum simulation. But the expected outcome we got it. Actual output also we got it. So now what will be the difference between the expected outcome and actual output? That and all we have to be identified. So finally, we just identify any small slight modifications or small error will be there in the sense we have to be identify the error. So that error, the quantum simulation, we have a second step. Step number 2 in the flows I just shown, identifying the random error. So what are the before that you have to be understand about what are the error. So error identification will be the second step, and error correction will be the third step. So what are the type of what are the different types of the errors are available in the quantum system? Number one, it's a bit flip error. For example, my flip value will be the 0, but it will be shown as a x. It's called as x error. That will be differently. It will be shown. For example, I am setting a value of 0 1, but it will be shown as a 1 0. I mean, the data it will be flipping, right? So bit flip. That's called bit flip. So my flip. I mean, my bit value is a 0, but it's flipped as a 1, changed as a 1 wrongly. Then our entire data it will be getting as a error, right? So that's called this type of the error. It will be called as a bit flip error, and also in the quantum system we can call as the X error. And Z error. What is the Z error in the sense? Phase flip error. Yeah. Once I'm setting, it will be coming as a 0. Here it will be coming as a 1, but that minus it will be coming. So the phase only it will be flipped. Bit it will be the same only. For example, 1 in the sense 1 will become, but phase only it will be flipped. That's called Z error. And Y error, in the random error, we have a Y error. That what is the Y error in the sense? Both it will be happening. Even bit also it will be changing. That flip also it will be changing. Okay, so the phase also it will be changing. Phase also it will be changing. Bit also it will be changing. Then it will be called as a bit phase flip error. It will be Y error. So here you can see 0. It will be given as a 1. I mean that data that expected outcome it will be. I mean we are expected to 0, but the actual outcome we got it as a 1. And also that part it will be the negative part it will be getting. Okay, so these are the different errors will be there, and then deep polarized error will be there, and then different mixed state. So actually we expected for the 0 and 1, but it will be provided as a different data, or 3-bit instead of 2-bit data we will be getting as a 4-bit data, 8-bit data, mixed states of the error we are going to be getting. So here 4 type of the errors are available in the quantum system. Quantum simulation while you're doing simulation. Here how to identify the how to rectify the errors. So you are getting a X error or Z error or depolarized errors, or what are the Y error, what are the error you're going to be getting, how to identify it, and how to apply the solution for the errors in the sense. So we have a few more steps for identifying the error. So first of all, we just identify the error, and then second one, we have to identify the probability of the error. So how much percentage, how much mixed states will be there? It may be the 0.1 or 0.5. How many percent of the informations are mixed to one? That and all you have to be identified, and apply the error channel. So based on the error channel, we can identify finally the output state. Our output state and input state it will be the equal in the sense that there's no any error, or else in the particular field the similarity will be not getting. I mean. Expected and actual outcome. The actual outcome and expected outcome have a slightly similarity in the sense. Then the original state it will be getting reworked, or else we can go with the regression. So again, we have to do for the regression. So even in the software testing, we have a concept called regression testing. So again, we have to do rework or requirement engineering. In the requirement engineering, again we have to be changed. So any slight difference will be there. Maybe it may be the a bit error or bit phase error or flip error. What are the error it will be identified? It has to be rectified. So these are the informations. So here one simple example you can take. So I have a 2 qubits. The 2 qubits it will be stored in the row. And then here I'm just setting based on the formulations. These are the input states. The row of 1001 it will be added. And if we are doing as a depolarized channels in the sense, here in the output states it will be says as a 0.95. So then our expected, I mean our input and as well as the expected outcome, there's a slightly difference, 0.1 difference will be there. So then it will be the error, it will become. So wherever, what are the applications? So if we are doing as a such a error identification we are doing, and then bit error identification we are doing, phase error identification, depolarized channels of identification we are doing. So what is the purpose why you are doing these? Are the error corrections or a test case? It's not really test case, it's a test case related informations in the sense. So identifying the quantum errors. Basically in the particular quantum system, what are the error will be there. And then communication. So even whenever you are doing a transmission the data from one end to another end, the communication problem it will be happening, right? So for avoiding the communication problem, and very most important, it will be the hardware testing. So if you are just doing simulation, so error simulation, the step number 2, the error simulation you are doing this is you can identify what are the hardware error will be there, and whether the given algorithm it will be perfectly working or not for the expected outcome. Because in the algorithm stage itself, we have just identified what will be the expected outcome and what will be the input. So whether in this particular algorithm it will be provided the expected outcome or not. If it's not provided in the system, then you can rearrange a mistake in the bit phase or mistake in the phase lift or other things. Okay, so you can identify and then estimate the estimation of the resources, how many resources are needed for the particular qubit operations. So these are the application areas of your random error checking. And so this is a process that will be called as a random error checking. Even yesterday's class also I said the related to the Pareto principle. If we are 100% of the coding will be there, 20% of the data it will be checked in the sense 80% of the error it will be identified. Similarly, in the simulation of random error checking, if we are doing in the sense for the 20% of the coding or 20% of the quantum system we are doing for the error checking in the sense, 80% of the problem it will be solved. The algorithm stage itself, the problem it will be sorted out in the sense surely you won't get much more resource based. All those things we are going to be avoidable. So again, I just recall the steps. The number one, CBTP map, it will be completed, and error identification, random error identification will be identified. So it may be the flip error or face error, whatever thing, it will be identified. So there's no any error. So right now that we have the trace map, and then error identification process also completed. Once error identification process completed, this is our third step and also the final step for our quantum simulating the quantum channel is measuring the reliability of input and output. So how reliability will be there for the input and output? In this place only we are focusing for our validation process. So in the validation of quantum simulations, expected outcome is available, and also the actual outcome also available. Both we have to be validated whether both the data are verifying or not. I mean validated or not. Actual data and expected outcome it will be qualified or not, both are same or not, that one we have to be identified. Here again we are coming for the measurement. So that what are the trace difference will be available, that will be stored in the TR place, and actual expected outcome it will be available in this space with above the trace simulations. So both it will be equal to zero in the sense there is no any error. So both are, I mean, your reliability of the input state and output state, there's no any error. Reliability will be available, or else we have to be available. Here you can see one more example. Again, I'm just sending one qubit states, 2 qubits states we are going to be inserting as a row. Here, these are the input state 100. As per the formulations, we are just formulating here the field data, the simplification of the field data of where two qubits will be getting as a 0.95. Then it says that 95% of the data, 90% of the 95% of the input and then output states it will be the similar. So we have a deficiency only for the 5% only. The 5% of the deficiency will be there. So, but 90% of the similarity will be there for the expected outcome and actual outcome. So these are the expected outcome. It will be it will be identified in the quantum simulation designing itself. So what will be the outcome? It will be coming. what will be the data it will be coming, everything it will be identified in the initial stage at the time of the quantum requirement analysis itself. But this 5% of the errors, 5% of the problem only we have it get. So this one it will be identified. So what are the major application of your identifying the reliability of input state and output state? Why you are doing as a third step? So the first step, the trace transmissions, as per our diagrammatic representation, the CBTP map, it will be traced for the backup and recovery purpose, and here random error it will be identified. Here reliability measurement it will be identified. So why we are doing as a reliability measuring the reliability in the sense, again we are for the error corrections, quantum systems error corrections. So efficient error corrections needed, right? So simply we cannot do the error corrections and at the time of the delivery of the product. So each and every stage we have to be identify what are the error corrections will be there. And transmissions, yeah, the quantum simulation, it will be the process of identifying the how the qubits it will be transferring from one end to another end. So the transmissions of the data and yeah, cryptography, security analysis, and testing of algorithms. So measuring it will be helpful for different phases. So and then here some more applications of your quantum systems simulations. So different quantum simulations, sorry, applications of the quantum simulations will be there. So the quantum communication. So whenever you are doing a different phases of the communication, so that quantum simulations it will be the major role. And storage. So even the last class also I explained it, today also I explained. You are doing a entanglement and superposition data in the sense at the same time your quantum systems are giving as all probabilities, right? So if I am giving if I just ask the quantum system to identify my 4-digit pin number in the sense, all the possibilities of 0 9s it will be given at the same time. So at the same time, the data that will be provided in the sense we need a much more data storage, because even for example, you just take the 4-digit pin number, it will be provided as a 1 lakh different combinations it will be provided. So 1 lakh different combinations we have to store it in the quantum system. So actually the only one pin number, that pin number I know, what is my ATM pin number I know, but that pin number the quantum system need to be identified. This is just example only. The quantum system need to be identified in the sense remaining all the data it will be occupied some more variables. Some more variables it will be occupied some more storage capacity, right? So all the swings you have to be ready. So reducing the resources, we need to be understand about the quantum simulation, because what will be the input, what will be the output, what will be the expected outcome, what will be the expected income, what will be the process it will be happening, everything we can understand. Then only you can reduce the storage, reduce the communication channels, and reduce the communication informations, and also the storage also we have to be doing. So quantum storage is the process of reducing the resources in the particular states of the qubits. Okay, for example, I'm sending a 5 qubits in the sense it will be compressed, it will be reduce the storage of the things. Only it will be checking for the, it will be asking some more question, or it will be identifying some more data. If it's very I mean it will be taking much more storage for the 0 to 9 combination in the sense, then it will be go with the, it will be asking, or it will be inquiring about, or it will be searching for what are the you can tell me any two numbers for your ATM pin number. I'm just telling my ATM pin number is a combination of 1 and 2 only. Then your burden will be reduced, right? So similarly, the similar concept it will be used in the quantum storage also for reducing the data. So then quantum information processing. So that compression, yesterday I explained about the compression algorithm. So it will be the major helpful for the optimization of your quantum algorithm, reduce the cost, handling the quantum system, and efficient handling of your qubits. So the qubits, it will be provide the multiple data, but storage it will be the major problem. So we'll see in the end of the things. One slide. Limitation will be there in the quantum simulation. That is where hardware related things. So all the resources storage it will be the major problem in the quantum system. So and then the quantum communication theorem it will be helpful for communicating the data from one end to another again. So here some more applications of your quantum information systems capability of your channel capability, identifying the transmission speed. So quantum channels, it's quantum channel. It will be the transmission of information from transmission of qubits from one end to another end. This transmission of qubits from one end to another end. What is the capability, or what is the transfer speed for the one place to another place? That and all it will be identified, and direct coding theorem will be there, and error identification. So these are the different areas of informations are available for your quantum simulations. So here, direct coding theorem. So the direct coding theorem is one of the major application for your quantum simulation. So this one, it will be identified what is the maximum rate of your quantum channels it will be traveling. That is the transmissions or relationship between your quantum channel and other informations it will be provided in the direct coding theorem. So this direct coding theorem, it will be providing the information to how the capability of the error handling, what is the capability of the error handling, and what is the data can be used in the what are the informations can be used in the particular data, whether it will be increased or not. All those things it will be given. So basically, that direct quantum direct coding theorem, it will be added with the encoding and decoding process for data transmissions for the security reasons. It will be adding over there. And then again, that quantum direct coding theorem. Why the direct coding theorem? It will be provided for the efficient accessibility of the data transmissions. So here you can see the comparison, or you can identify the comparison of how your quantum simulations as well as classical simulations, it will be the slightly different. So here the nature of your quantum simulations, it will be qubits. Quantum mechanisms it will be using, right? So in this quantum simulations, the framework, basic underlying framework, it will be the quantum mechanism. But here the classical system. So if you are using as a zeros and ones, the two combination of the two combinations only, it will be applicable for your classical simulations. But in the quantum simulation, if we have a superposition and quantum mechanism, you can use it. So different data we can use it. So yesterday I explained about the entanglement and then reverse operations also. So in the reverse operations, what are the data will be available in our one hand. The opposite directly it will be identified. Okay, so the pair of gloves, with the pair of gloves, I explained all the components of your quantum mechanism related information, and what are the mathematical tools can be used in our quantum simulations. In the sense, yeah, quantum states will be they will be using, but here classical states only the operators of basic operators only they will be using for your tools. And then here qubits, it will be playing a major role in the quantum simulations. Here we are just using a qubits and superpositions, entanglement, and other flipping data, everything we are just using for your quantum simulation. But here classical bytes only, they're again binary system, zeros and ones only. We cannot do the simultaneously for the multiple process in the classical system. So, but here we can use it as a superposition and entanglement. The superpositions, it will be says that what will be the what will be happening. For example, I am thinking it will be the one, the output expected, expected outcome for the particular qubit, it will be the one. If zero, what will be the happen? If actually my expected outcome, it will be zero. If one, in this is what will be the situation. And if at the same time zero also not there and one also not there, what will be the particular position? So these are the different combinations of the different informations are possible in this quantum simulation. But here only we have it as a zero, whether yes or no, or zero position or one. My expected even again we are coming for the test case generation. My expected outcome for the addition of two number a plus b equal to c, in the sense it will be the c. But suddenly it won't be happening, in the sense it will be says as the test cases will be getting failed. Again you have to be redo. Again you have to be redo the similar test cases or different test cases. The error in the requirement analysis, anywhere you have to verify. But here what happened, that superposition will be identified. What if the expected outcome is one, but you are getting a zero, in the sense it will be mapping with the 0 and different data. Based on the superposition, it will be adding to the different data, so different informations it will be adding. So these are the different aspects we can get it in the quantum
Yuvraj sir,
simulations.
Yuvraj sir, kindly mute the audio.
Yeah. So here different positions or different datas can be added over there. So given my input values is 0 and 1 only. So all the possibilities 1 1 0 0 0 1 1 0, all the possibilities can be added in the quantum simulations. So and then here I mean cloning, that is parallelism is applicable for the superposition and quantum simulations. So yesterday also I explained about the two pair of gloves. If one pair of gloves is available, two persons are taken in the sense one person will be getting as a left hand gloves in the sense, opposite person obviously it will be getting as a right hand gloves only. There's no any doubt. So no need to see the things. If the person A, it will be getting right hand in the sense, person B will be getting as a left hand gloves only. It may be the different part, a different position. So the parallelism will be available. So because of the parallelism concept only, we can use it as an entanglement. So what is A and then A dash will be there, and what are the both it will be doing here. Here the process it will be moving in the sense, what will be the opposite process it will be moving. We can say from in your place itself, that is in your position itself. No need to verify the other things. So then only it will be time, it will be taken much more, right? For example, in this classical system, there is no any parallelism achievements, I mean cloning process is not available. So if you are I mean that expected outcome is 0, but 1 it will be getting in the sense the process will be stopped. It won't think in different formation. My expected outcome is 0, but I'm getting my actual outcome is 1. So a test case is failed. That's all. My test case is failed. That's only full stop. It will be given here. But here, it won't. It's not like this. My expected outcome is 0, but I'm actual outcome I'm getting as a 1 in the sense. It will be again. It will be checking whether 1 or in superposition. Incidentally, head or tail or superposition will be checking, or other combinations. Is 0 with the 0, any flip position will be available. I mean it will be getting -1 or minus informations or something, flipped informations are getting, or anything. All those things it will be verified in the quantum simulations. But here the classical simulations, that at all it's not at all verified. So only it will be identifying based on the classical bits of zeros and one, either yes or no. That is your binary systems based only. It will be identified. So that's a thing. And efficiency difference of between your quantum simulation and classical simulation. So here it will be more efficient because we have a trace matrix. Trace matrix we have it, gentle measurement, and then other different theorems will be a habit for the quantum trace. Because trace simulation or trace quantum trace will be the major component for identifying. Even the last class I said the R map. Okay, so today the CTP map, both the maps it will be taken as a traceability. So traceability it will be the more efficiency. So all the complexity it will be explore, or any problem it will be happening in the sense also, everything it will be everything it will be taken care by the quantum simulations. But if we are the classical simulations, if we are taking, it will be the there's no any efficiency. It's not we cannot say there's no any inefficient data are available, but it will be compared with quantum solutions. It will be inefficient. So that's a thing. And the quantum systems have many particles. So the many particles it will be the major component for your quantum systems. So in the initial explanation, I mean initial class itself, I explained the quantum system is not limited to the I mean one number or 100 number or 1,000 or lakhs of information. It's the n number of the informations. So n number of the informations are getting in the sense, n number of the data need to be stored, n number of the data need to be compressed, n number of the data we need to be identify the solution. So the different data, so different particles need to be stored. So the major limitations of hardware will come. The next slide it will be explain you what is the limitation will be there. The major limitations of hardware, but number of particles will be there, different data storage will be there. So easily you can explain all the informations. But here number of particles it will be there very restricted. And application oriented, especially for the quantum simulations, is not only the information theory. As a topic, yesterday and today I am explaining about the information theory related. Apart from the information theory, it will be the more helpful in the material chemistry and other places also. It will be more helpful in this quantum simulations, especially the quantum simulation will be coming to the information technology. It will be more suitable as well, because you just consider day by day how many users are they using in the Google, how many users are looking for the information in the chat GPT, how many people are looking for the, so how many respondent will be needed. The each system, it will be responding to the multiple data. This is not limited. It's a huge number of the data we have to be identified for telling a one solution. Even we have a concept called direct interactions and other things. They are already feeded informations, right? So that will be provided as a some feeded. For example, we are looking for the data directly, and what the input and what the output, that will be in the classical simulation. So if we're just telling to the banking chat box hello, in the sense they will be telling what will be happening, that's already feeded input, what is the output. But here quantum system is not like this. It has to be think in different formation, different data, different classical informations. We have to be thinking. Even uh, that simple quantum simulations will be happening in the sense either in the superposition also they have to be thinking, and different identification that will be do. So the application areas is not restricted only for the information theory. It have larger application areas, especially in computer science field, as our Gopi sir has pointed out in the initial stage. So in upcoming grow, it will be related to the information technology. The quantum system, it will be including in information technology, information system. It will be the more advantage and more focusing in this application area. And here, very limited application areas only available, even for the engineering systems and all those things. So here, some more application examples like weather forecasting and other things are available. But here, based on your quantum simulations, you can do the larger modeling. So modeling of the information is very important, right? So simply we can explain. For example, it's a process between the account holder and the bank managers. In this, directly we can explain with the different explanation. Or if it's a university ER model or university diagrammatic representation you are giving, yeah, we can explain. But you can see how our quantum system it will be explained, or how quantum system data it will be explained. It's very difficult to identify the data, right? So here the modeling, it will be the very easy when we are using as a quantum applications. So and finally the what are the limitations? So the major limitations I'm focusing here in this quantum system, it will be the hardware. So because our number of possibilities is very high. So even our input is a 0 or 1 in the sense, it will be setting all the possibilities at the same time only we are focusing. At the same time it will be focused, so time it will be taken. For the classical system, it will be provided as a 0 1 1 1 1 1 of multiple times it will be taken. But here time it will be reduced, but you can see how much this, because only one it will be the correct output. All right. For example, again, I'm coming to the ATM pin digit, four digit pin number. Only one pin number it will be the correct. If I'm asking, I will tell what is my ATM pin number. But if I'm telling to the quantum system or other components in the sense, it will be generating multiple data at the same time. At the same time, it's one of the advantage. We are focusing quantum simulations for the same time, but how many data it will be storing? So our limitation is a hardware. So hardware limitation will be the major problem we are focusing. But here, widely the hardwares are available, no issue for the, because each and every time that variable it will be changing, right? So first time it will be changing, sending to the 001, and variable it will be erased, data it will be erased. Again, second time it will be sending as a 001, different variables, the same memory location will be happening. The 2 MB only, the 2 KB data only, it will be changing as a 0 0 0 0 1 1 1 1, all those things. But here it's not like this in quantum computing. Quantum computing, what happened? It will be sending a multiple data at the same time. So different probabilities, not as a different probability. All the probabilities of the particular input it will be sending. So all the probabilities it will be sending in the sense that storage it will be the major drawback we are getting right now as a study of your quantum simulation. and efficiency of the system is very good, and the limitations are there's very much more limitation, and qubits it will be playing a major role in this system. So here again, binary systems it will be playing a major role. So what is the strength? Yeah, we have efficient data accessibility will be there, larger data accessibility will be there, error identification is very easy, and parallelism, that is where cloning it will be very easy, and especially the quantum systems, whenever we are focusing for the cloning, that is where data, the same data we have to be used for the multiple stages, then quantum system it will be the more advantage. Here in this classical simulations, and the classical simulations they have a different reliability of the classical systems will be there, and it will be the well data will be available. There's no any error in the hardware, or I mean difficulties or limitation in the hardware, but here the limitations only I'm focusing for the hardware limitation only. So this is about related to the a comparison of your quantum simulations and classical simulations. So here related to the how the simulations, especially, so basically simulation channel. I mean, sorry, simulating your quantum channels in this, they have a three steps. Step number one, we have to be identify the CPTP map to so that traceable map it will be identified and it will be located. What is the data and what is the informations are available, and here identify the random error. So in this random error, the random errors can be classified as a 4 or 5 types of the error. That is where bit flip and phase flip error will be there, and bit and phase flip both error will be there. Depolarized error will be there, right? So this is our second stage of your quantum channel simulation. The third step of your quantum channel simulation, that will be the output. Identify what are the reliability of your input and output for the particular phases. So this quantum channel simulations, it will be holding a three steps. These are the components I explained for the last 30 to 45 minutes. So here the comparison of your simulations, I mean the quantum simulation and classical simulations, what are the limitation, efficiency, applications oriented, what are the different advantages, everything will be explained. So here I just uh, provided to the online quiz. So how you understand for the quantum simulations. So just share the link to the chat box. It's a 10 minutes test, not 10 minutes. It may be the 5 minutes only. Just 10 questions only there. I can understand how the participants you can understand. Just share the link in the chat box. Or you're not getting the link, you can scan the QR code, you will get the link. For the next 5 minutes, you can attend the quiz, and then we'll discuss the quiz answer in the sheet itself. I'll be taking any one of the faculty members' quiz answer, and then we'll discuss. So the link is available in the chat box. You can click the link, or you can scan in the mobile. You will get the link directly. The scanner it will be redirect to your system or your mobile phone to the online quiz. Just 7 or 8 question will be there. You can answer. You can read the question and answer the questions. I will be provide the solutions. Even you can view the answers. I explain in the end of the section. So the question is available. Anyone? You can able to see the questions in the link.
Yes, sir.
Oh, okay. link, please. Yeah, I will resend the link again. You don't have any mark for the quiz, just for how you understand. That's all. Okay, no mark, uh, no certificate mandatory, but you can attend. Then I can understand how you understand all the topics.
Participant, if you have any queries, you can ask now.
At 8:35, we'll discuss the answers and also the quiz questions and answers.
Dr. Mani, sir.
Quiz is done, sir.
Dr. Mani, sir, I think all the participants completed the quiz. You can share the answer now.
Yes, sir. Yes, sir.
Yeah.
So I just share the screen of the respondent details. It's visible. Gopi sir, it's visible right now. Yeah. So I just take any one of the person's information, or we can go.
Participant, if you completed means, you can follow the answer.
The answer they are getting in this link itself. I just explain the things with the summary. Yeah. So here the screens are visible, sir. Gopi sir, my screens are visible.
Yes, sir.
Okay. So what is the essential part of your predictive data? So 11% of the faculty members are mentioned as a classical computation. So wrong. Actually, the right answer is quantum simulations. So quantum simulations only it will be provided the predictive of your data. So whenever you want to be predict what will be the expected outcome, what will be the expected outcome, then we have to be do with the predictive things. Okay. So the quantum simulations will be the correct one. So and then some modeling simulation will be provided for the informations and explore the capability of the data, not for optimization technique. It's a modeling simulation. So and here this one I explained with the diagram. Today's major topic only. This is a topic. The quantum channels only will be describe how our data transmissions are available, how the data transmissions are moving from one system, one place to another place. Even I explained with the diagrammatic representation, each and every qubits, how the transmissions will be happening. This is then we have to be identify the quantum channel. The quantum channel only the right answer. So here again 62% of the faculty members are mentioned correctly. Only few faculty members are mentioned it's a wrong answer. But the quantum channel it will be describing the how the transmitted it will be happening. And here which map it will be helpful in our simulating the information. So that is a CPTP. So R map, yesterday we discussed about the R map that only applicable for your information related. There's really modeling concept here. Only the CPTP map it will be helpful for your analyzing the simulation, analyzing the simulation, and also analyzing your quantum systems. So whenever you want to be analysis, what's the input process, what will be the output, and what is the data will be there, then we need to be identify the CPTP map. So here also 77% of the faculty members are mentioned as a CPTP. Yeah, remaining 11% only they mentioned as a wrong answer. And here what will be the stage of the your third simulation? So that is whenever you are creating your quantum channels, what is the third stage? So we have to be identify the reliability of the input and output. So what will be the expected outcome and expected income input, and what is the actual outcome we are going to be getting, even in the based on the software test case I explained. So in this software test case, we will be getting as a expected outcome in the particular quantum channel, but the data is not at all getting, the data or information is not at all getting properly in the sense the reliability it will be the major issue. And then why you are just reducing the resources, why, for what purpose we are reducing the resources, that's a question. This one the reducing the resources for storage of your quantum informations, because the quantum resources are very larger one. For transmission of the data from one end to another end, we have to be reduce the data. So for why we are reducing the informations in this sense, for the quantum storage one. So here the next question. So even here also 75% of the faculty members are mentioned as a correct answers, and here one few faculty members only it will be the wrong answer they mentioned. Okay. So and then here the quantum noisy coding theorem, it will be describing coding and decoding of informations. So this one, there's no any communication or protocol or resources or data related informations. Only that coding and encoding. Because why we are doing as a coding and encoding for the quantum informations or quantum coding related to the things in the sense, because of your data accessibility and security purpose. For the securing the informations, we are just doing as a quantum related coding and decoding data. So, and then what is the major limitation? This one, the last slide also I explained what is the major limitation in our quantum simulation in the sense, the comparison of your classical simulation and quantum simulation discussed about. The hardware, it will be the major drawback. The 57% of the participants are mentioned and hardware. The communication, there's no any error in the communication. Only the hardware it will be getting a problem. And protocol, there's no any protocol error, because the quantum, wherever the data are increasing, the number of data, the number of informations are increasing in the sense also, your protocol it will be increasing. I mean, the protocol security it will be increasing. Trace also, there is no any error won't be coming, because what are the data will be available, we have a very efficient trace matrix will be there, and trace quantum trace informations will be there. So all those things it will be helpful more efficiently in our data transmissions. So in our quantum simulation transmission, so there is no error in the there's no any much more difficulties or limitation in the trace matrix also. Communication also, transmissions will be there. Majorly, why we are doing a quantum simulation in the sense for the transferring the data, or for understanding the purpose of the quantum system, how the input and output and what the process will be there, what are the error will be there. We discussed about the majority of the bit error and bitwise error and all the phase error will be there. So for understanding different bit errors, so we are just using a quantum communication. So there is no any much more limitation in the quantum communication. Only the limitation is available in our hardware part only. So that will be obviously it will be getting, because that's the thing I said. So suddenly um, uh, yeah. Obviously we are getting a larger data. We are getting larger data in the sense, then we cannot yeah, the larger informations we are getting, larger data we are going to be storing in the sense, hardware problem is always it will be coming. So this is a thing, I asked hardware problem. What are the major problem in this is hardware, it will be the limitation, major limitation in our case. So this is my final conclusion about your quantum simulations. So basically, we have a classical simulations and the quantum simulations also. So the quantum simulations, it will be helpful for understanding the quantum computing in our information theory. So basically, the information theory, it will be a very limited one. So larger data we are going to be dealing, larger informations, each and every data it will be acting as a one new qubits, multiple qubits it will be adding. Yesterday we discussed about the composite qubits, and then we are adding a multiple composite qubits. In the sense, what will be happening, exact data it will be unable to identify the exact data. So unable to identify the exact data, we need a purification. So yesterday I explained about the purification theorem. The purification theorem will be explained. Divide the mixed qubits to the single qubits. So they have a lot of different or entangled qubits will be available. Then it will be divided as a single qubits. So the single qubits it will be the purification. So the purification and trace matrix, quantum simulations, a lot of different simulations it will
तो वो
be
चाय कौन सी
helpful
पिक्चर है
for your quantum
दो
applications. And then here
कौन सी पिक्चर है जी
the classical simulations it will be we have restrictions. Yeah, this one in the beginning itself I explained, we have zeros and one combinations only. So it will be the bit limitation will be there. But here there is no any limitation, because we are using a superposition, entanglement, and reflection will be there. Trace matrix will be there, and gentle measurement will be there. Gentle measurement, it will be the another major advantage in our quantum information theory, because if you're not using a gentle measurement, that then all the probabilities we have to be verified. So the number of probability will be increasing. Again, I'm coming to the 4-digit ATM pin number. Number of probability will be increasing. So number of probabilities, it will be increasing in the sense our space, we need to be allocate the new spaces for the number of probabilities. So increasing the number of probability, it won't give the solution. That's a final conclusion related to the quantum information theory. So yeah, it's one of the advantage. All the probabilities, it will be provided to the at the same time. The solution will be given because all the probabilities is coming. But all the probabilities handling, it will be the major difficulties in our quantum system. So right now, much more focus in the advantages of the quantum computing. Advantage only. Advantages of the quantum computing, it will be handling large data, efficient data, efficiently, it will be accessibility, trace matrix will be there, everything will be there. But the hardware limitation will be the major problem. Maybe it will be coming to the solution how 10 or 15 years before we are getting a problem in our storage. Then cloud technology will be came, and with the cloud technology will be reduced all the problem whenever we are going to be storage problem. Previously in Google, they won't provide much more. 15 years before, if you are using a Google, they provided a very limited storage only. Right now, they are providing much more data. Even right now, we are going to be getting after cloud technology will be implemented, that storage data will be reduced. Similarly, in quantum information theory also, the hardware limitation will be expected to overcome. So that's a final thing. And then we just comparing with the classical simulations or classical information theory. The quantum, it will be the emerging technology, and it will be more helpful for our future things. Thank you very much, all the participants. If you have any queries, you can post the message in the chat box. I will respond.
Thank you so much, Dr. Mani sir.
Yes, sir.
Participant, if you have any queries, you can ask now, or you can post in chat box, or you can mail, or you can ask queries in WhatsApp also.
Yeah, I will share my PPT to the organizer. Organizer
Yeah,
will
sure, sir.
upload all the PPTs in your end.
Oh, yeah, sure, sir. We will share the PPT for all the session to WhatsApp group, as well as they can retrieve information from the Atal FDP also, Atal FDP portal also.
Okay. Thank you. Thank you very much. In chat box, I'm getting a thank you message only. There's no much more questions. Okay, no issue.
Thank you, Mani sir.
Okay,
Thank you
sir.
for your wonderful presentation.
Okay, sir. Bobby, sir, finally, I just give my thanks to organizer of the FTP, 60 FTP. Actually, the attending FTP is very easy, right? All the 6 days, everybody can attend and you can get the knowledge. Even for the presenting the PPT for the 1 or 2 sections only, all the resource persons will be presenting. I presented for the 2 sections very convenient, but organizing a 60 FTP, it will be a difficult job even for identifying the resource person and arranging all the components, especially for the timing. All working professors, faculties in all over India. So
Yes,
we
sir.
have a time in the 6:30 to 9 only. So the efficient accessibility, it's very good. So I thank to organizer of the faculty development program, 6-day faculty development program, Dr. Gopi, uh, HOD Department of Computer Science, Dhanalakshmi Srinivasa Engineering College, and also a very thank you to the host institute of the FTP. Thank you very much, sir.
Thank you so much, sir. Even though the participants are very eager to attend this FDP in the evening time also. The ACT Atal FDP is organizing evening time, but the
Okay.
participants are very eagerly to attend the FDP, even 6 to 9. Even though they are moving their home, but they are
Okay.
interested to attend the FDP because only of this new technologies only, sir.
Yes.
So the quantum computing is going to rule the world, and it will be booming nowadays. So it
Yes.
will be, I think, the participants are more eager to attend this FDP, sir.
Yes. Okay, sir.
Anyhow, thank you for your wonderful session for yesterday and today also. Thank you so much. We will meet again one more FDP if possible in Hotel or what it may be. Thank you so much, sir.
Yes, sir. Thank you, participant.
Thank you,
very much, sir.
participant. Thank you so much.
Thank you, sir.